Hi everyone. In this video, we are going to go over chapter 11. This is the synthesis chapter in your textbook. So if you have the third edition of the textbook, it's chapter 11. If you have the second edition, it's chapter 12. Now, in synthesis, we're really trying to figure out how do we get from point A to point B. And there's a lot of different types of synthesis problems we might have. Maybe we want to change where a double bond is located. Maybe we want to change where a halogen is located. Or maybe we're starting out with a really small chain of carbons and we want to lengthen that chain of carbons. Now, in your pods, you've already gotten some practice with synthesis. So in this video, let's go over some of the trends that we notice in synthesis problems. Okay, so let's start with the position of a halogen on a molecule. What if we want to change where a halogen is positioned? So for example, let's say we start with a bromine on a secondary carbon, and we want to move that bromine to a tertiary carbon. How do we do that? Well, by now you might have noticed that in order to change the position of a functional group, you often have to perform elimination, then addition, then elimination, then addition. So you kind of go back and forth between those two until you get to the right product. So here what we can do is start with elimination. And that's going to give us a double bond. And notice that that double bond is between where the bromine was and where we want it to go. Then in the next step, we can perform addition. And we can add that bromine back onto our molecule, but this time it will be on that tertiary carbon. Okay, so let's actually draw out a map of what we would do in this situation. So I'm going to redraw our starting material, and then I'll draw our intermediate alkene, and then our final product. And let's try to figure out which reagents we would use to go from the starting material to the product. So if you want to pause the video and try this on your own first, you can. And then when you're done, you can unpause and see if you got it right. Okay. So how do we form an alkene from our starting material? Well, we already said we want to go through an elimination process, but let's also consider what type of double bond we have. Is this a substituted double bond? Is it not very substituted? So this is a fairly substituted double bond. Now, remember in elimination, we always want to try to find the alpha carbon that's bonded to the leaving group. And then we also want to consider any beta carbons because that's where we're going to lose protons. So we could lose a proton from the right-hand beta carbon, or we could lose one from down below. Now, if we lose the hydrogen to the right, that's going to give us our Zaitsov product. So remember, a Zaitsov product is a more substituted alkene. Now, what if we had lost the hydrogen down below? That would have given us our Hofmann product. And we'll go back to the Hofmann product later. So how do we favor the formation of the more substituted alkene, the Zaitsov product? What type of base should we use? So probably a small base, right? So that it can kind of wedge itself in and grab that hydrogen that's kind of in a bulky part of the molecule. So there's a few different options here. You could use NaH or maybe ethoxide, so NaOET, so sodium ethoxide. Anything that's small, really. Okay, so then how would we then go from our alkene to our alkyl halide? So we already said we want to do an addition problem here, or an addition reaction. And we want to make sure the bromine ends up on the more substituted carbon in the double bond. So I'm going to use HBr because hydrogen will add to the less substituted carbon, bromine will add to the more substituted carbon, and that's Markovnikov addition. Okay, so let's look down below at our Hofmann alkene, our Hofmann product. How would we favor the Hofmann product? So how would we favor the loss of the hydrogen down below on the methyl group? We want a bulky base. So just some options here. You can use potassium tert butoxide, or you could use DBN or DBU. So those are all bulky bases, and I'll just write a note up here. They're all bulky. So that will favor the Hofmann product. All right, so then let's say we want to add bromine to the less substituted carbon, so this primary carbon down below. How would we do that? So let's draw our product just so we can visualize. So if we're adding bromine to the less substituted carbon, that would be anti-Markovnikov addition. So we would still use HBr, but we would also add some peroxides. And that would be our radical addition of HBr, and again, that would be anti-Markovnikov. Okay. Now, one last question. What if we have our alkene up above, but we want to add bromine to the less substituted carbon on that alkene? How would we do that? Same thing that we just did, right? HBr and peroxides. Okay, so again, we just saw several different ways that we could move a halogen. So if we start with a secondary alkyl halide, we could form a tertiary alkyl halide by favoring the Zaitsov alkene, the Zaitsov product, so the more substituted alkene. Or if we wanted to create a primary alkyl halide, we could go through elimination and addition again, but this time we would use a bulky base to favor the Hofmann product, and then we would perform anti-Markovnikov addition to place the halogen on that primary carbon. Okay, so now let's talk about alcohols. How would we move an alcohol on a molecule? Okay, so let's say that we have a secondary alcohol. And we want to, let's say, move that OH group to this primary carbon down below. How would we do that? Well, this is very similar to the last problem. We want to go through elimination, create a double bond, and then perform an addition reaction that places the OH group where we want it to go. However, if we're going to perform elimination in this case, OH isn't a very good leaving group, right? It's a poor leaving group. So we have to convert that to a better leaving group. So maybe, for instance, we convert that into a tosyl group. And then we can perform elimination. And again, we would want to form a double bond between where the OH group was and where we want it to go. So that would go down below. And then we can perform addition to add the OH group to the less substituted carbon there. All right, and let me just highlight that carbon that we're interested in on all of these. Okay, so now let's redraw this and we'll figure out which reagents we need to use here. Okay, so I'll give you a hint. In the first step, we have 2 reagents we're going to use to create that double bond. And then in the second step, we want to move the OH group to the less substituted carbon. How would we do that reaction? And you can pause the video if you want to try this on your own first, and then we'll go over it together. Okay, so up above we said that we have to convert the OH group to a better leaving group. So we can add tosyl chloride and pyridine. So that will create that OTS leaving group, which is a good leaving group. And then we have to favor this Hofmann product, because remember, our alpha carbon is where the leaving group is bonded, and then we have 2 beta carbons. The beta carbon down below, that's kind of where we want to take a hydrogen and form our double bond, and that would be the less substituted alkene. So how would we favor formation of the Hofmann product? A bulky base, just like we saw on the last slide. All right, and you could also use DBN or DBU. So whichever one is your favorite bulky base. They all do the same thing. And then how would we add an OH group to the less substituted carbon on a double bond? Hydroboration oxidation. So we use our borane, tetrahydrofuran, and then hydrogen peroxide and NaOH. Okay. Now, what if we want to move the OH group to the tertiary carbon, so the other beta carbon? How would we do that? So let's draw what that would look like. Okay, so how do we make the Zaitsev product, or how do we favor the Zaitsev product? And then how do we add the OH group to the more substituted carbon? So if you want to pause the video and try this on your own, you can. and then we'll go over it together. Okay, so this is going to be a pretty similar process to what we did up above, at least in the first step. So again, we want to use that tosyl chloride and pyridine to make a better leaving group. And then we need a base to perform elimination. But this time we want to favor the Zaitsov product. So we're going to use a small base like sodium hydride or sodium ethoxide. Or another small base works too. Okay, so then how do we add an alcohol group to the more substituted carbon? Well, we could use acid catalyzed hydration. So H plus and H2O. So you could use sulfuric acid or phosphoric acid. Either one works. Or you can just write H plus in brackets. Or you could also just write H3O plus. That works too. Either one is fine. All right, so on this slide, we saw how we can move an alcohol group. Again, we're performing elimination followed by addition, but because OH is not a very good leaving group, we have to first convert it to a good leaving group. All right, now what if we want to move the position of a double bond? So let's say that we have the following. Okay, so we've got a cyclohexene group here with a methyl carbon on it, or a methyl group. So what if we want to move the double bond? So let's say we want to move the double bond onto this methyl group here. How would we do that? Well, we already have an alkene, so we don't want to perform elimination first. We actually want to perform addition first this time. And that's going to allow us to add a leaving group. And we probably want the leaving group to be on the carbon that's attached to the methyl group, because that will then allow us to form the double bond that we want. And in order to get that double bond, we need to perform elimination. So again, we're alternating between elimination and addition, but this time we start with addition and then go to elimination. Okay, so let's kind of walk through this process and figure out which reagents we would need. Okay, so if you want to pause the video and figure out which reagents to use for this reaction, feel free. And when you unpause, we'll go over it together. Okay, so how would we add bromine to, let's see, the more substituted carbon on this double bond? How would we add bromine there? So we would use HBr. So hydrogen adds to the less substituted carbon, bromine adds to the more substituted carbon. So again, this is Markovnikov addition. And then how do we perform our elimination step? Which base should we use? So let's find our alpha carbon. And then let's find our beta carbons. Okay. And let's see, we want to try to take a hydrogen from the beta carbon on the methyl group. And how would we favor that? So is that the Hoffman or Zaitsev product? That's the Hoffman product because it's the less substituted double bond. And how do we favor the Hoffman product? With a bulky base. So again, you can use potassium tert butoxide or DBN or DBU. All right, now what if we want to add bromine to the less substituted carbon on that initial double bond? How would we do that? Well, we would still use HBr, but what do we need to make sure that it's anti-Markovnikov? Peroxides. Okay, and then in our next step, what if we want to move the double bond there, kind of towards the bottom right? Well, again, let's find our alpha carbon and our beta carbons. And let's see, the beta carbon up above, that would give us a more substituted alkene, right? Because let's say we had a double bond there. That would have 3 groups attached, but a double bond down below would only have 2 groups attached. So this is still the Hoffman product. So we need to figure out how to favor the Hoffman product. So which base should we use? Same as we did above. Some sort of bulky base. Okay, so on this slide we saw how to move a double bond around a molecule. And again, remember, you always want to consider, am I forming the Hoffman product or the Zaitsev product? So you can kind of compare your beta carbons and what type of alkene you would get depending on where you deprotonate. All right, so next let's talk about how to go from an alkane to an alkene to an alkyne, or how do we go from an alkyne back to an alkane? How do we do that? So I'm going to draw just a really simple triple bonded molecule here, a really simple double bond, and then we've got our alkane. So let's figure out, how do we go from a triple bond to a double bond to single bond, and then how do we go in the reverse direction? So if you want to pause the video and try this on your own first, you can, and then we'll go over it together. All right, so let's start with the top arrows. And we'll start by going from a triple bond to a double bond. Which reagents could we use? So there's a few different reagents we could use depending on what type of double bond we want. So what if you want a cis alkene? Which reagents would we use? So we would use hydrogen and a poisoned catalyst, such as Lindlar's catalyst. What if we want a trans alkene? What would we use? Dissolving metal reduction, so sodium and liquid ammonia. Now, you'll notice in this case that we don't have any substituents on either end of our double bond. So we could use either of these to get our double bond because we don't end up with cis or trans in this case. But in a lot of other cases, we do have to consider whether we need it to be cis or trans. Okay, so then how would we go from a double bond to a single bond? Hydrogen and some sort of catalyst like platinum or palladium mixed with carbon or nickel, that works too. And then remember that you can go from a triple bond all the way to an alkane using hydrogen and platinum or palladium and carbon as well. But if you want to stop at the alkene, that's where you have to use either hydrogen with Lindlar's catalyst or dissolving metal reduction. All right, so now let's figure out how do we go from an alkane to an alkene? So how do we go from a single bond to a double bond? Well, we're essentially performing an elimination reaction, right? But we need to add a leaving group first. So one way that we could add a leaving group to a single bond is to use our radical reaction, Br2 and light. So that will add a bromine to that single bond. And then in the next step is where we can perform elimination. So we could just use a small base here. And of course, there's a few different small bases you can use. All right, then once we have our double bond, how do we get to a triple bond? Well, remember, in order to make a triple bond, an alkyne, we need to create a dihalide. So if we want to create a dihalide from a double bond, we can just add Br2 across the double bond. Then, in the next step, we need to eliminate both of those leaving groups, and that will give us our triple bond. So remember, we want to use a strong base like sodium amide, and we'll use excess sodium amide. And then remember, at the very end, we would have a negative charge because the excess sodium amide would grab any hydrogens possible because it's such a good base. So in order to add a hydrogen back on there, we need a weak acid like water. Okay. So lots of options here if you need to go from a triple bond all the way to a single bond, or if you need to create a triple bond from a double bond, etc. So there's lots of different things we can do here. So let's just talk in general about how to approach a synthesis problem. Now you've already kind of learned this on your own going through the pods. So you've got a little bit of experience with synthesis, but let's just kind of summarize how to approach those problems. So number one, let's say that you need to make a change in the length of the carbon chain. So let's say that you need to reduce the length. What's one way that you could reduce the length of the carbon chain? And then what if you need to increase the length? How would you do that? And feel free to pause and look through your notes to figure those out. So if we want to reduce the length of the carbon chain, one thing you could do is ozonolysis. Because remember, this is going to break apart a double bond or a triple bond, depending on what you have. And that means that you're losing some carbon atoms in the process. Now, what if you want to increase the length? Alkylation. So you could make a triple bond, and then once you have that triple bond, you can perform alkylation to add more carbons onto your carbon chain. And then two, we already talked about how you can change the location of a functional group, or you could change the identity of a functional group. Now, if you want to change the identity of the functional group, that's where all of our addition reactions and alkyne-related reactions come in. And let's actually go through an example problem where we might need to do some of these steps here. So let's say we want to start with an alkyne, and then we want to form an alkene. All right, so remember on each side of the alkyne are carbon atoms. Sometimes I like to draw little circles there so I can keep track of how many carbons I have. So if you want to pause the video and try this synthesis on your own first, you can. And when you unpause, we'll go over it together. All right. So the first thing that I usually do in these types of problems is I count my carbon atoms. Because if we need to reduce the length of the chain or increase the length of the chain, then that's going to kind of lead me in one direction or the other, whether it's ozonolysis or alkylation. Now, in some cases, I don't have to do anything to the length, and I can just skip ahead to step 2, change the location or identity of a functional group. All right, so let's count our carbons on the starting material. So we've got 1, 2, 3, 4, 5. And then let's check the length of the alkene chain here. So we've got 1, 2, 3, 4, 5, 6, 7. Okay. So we need to add 2 carbons onto the end of our alkyne before we form our alkene. Okay, so that means we need to perform alkylation first. So how do we perform alkylation? Well, first we need to remove that hydrogen from the end of the triple bond, and then we have to add a primary or methyl alkyl halide depending on how many carbons we need. So let's use a strong base like sodium amide to get rid of that hydrogen. So that deprotonates. And then in step 2, we're going to add a 2 carbon chain. So there's our 2 carbons. And then I'm going to add a halogen on the end. So it's a primary alkyl halide. Okay, so that will look like, let's see, that. All right. So we've now got 1, 2, 3, 4, 5, 6, 7 carbons. Great. It's exactly what we needed. Okay, so now we can change the identity of our functional group. So initially we have an alkyne, and we need to end up with an alkene. But also make sure to note what type of alkene you have. Is it cis or trans? So this one is trans because the carbon groups are on opposite sides of the double bond. Okay, so that means I need to use dissolving metal reduction to get a trans alkene from an alkyne. So again, here in step 1, we went from 5 carbons to 7 carbons through alkylation. And then in step 2, we went from an alkyne to an alkene. So that's just following the steps that we went through on the last slide, how to approach synthesis. Okay, now one thing that we've already talked about previously is retrosynthetic analysis. So let's do an example problem using this method. And remember, in this method, we work backwards. So we start from the product and kind of work our way back to the reactant. So let's say we're starting with an alkene, and we want to end up with an aldehyde. All right, so let's start from the product. And if you want to pause the video and try this on your own first, you can. And then when you unpause, we'll go over it together. All right, so let's start from the product, like we said. And let's just double check, how many carbons do we have compared to our starting material? So we have 1, 2, 3, 4, 5, 6. And our starting material has 1, 2, 3, 4. Okay, so at some point we have to add more carbons on. And then at another point we have to change our functional group to an aldehyde. Now, because we're working backwards, I'm going to draw these kind of bold arrows here, or these chunky arrows, because that will indicate that I'm going through retrosynthetic analysis. And this is just something a lot of textbooks in chemistry do. They use a different arrow to show retrosynthetic analysis. Okay, so if we're ending up with an aldehyde, let's see, what could we start with to get an aldehyde? Well, we do know some reactions where you can turn an alkyne into an aldehyde, right? So let's draw an alkyne, and it has to be a terminal alkyne, right? Because the aldehyde's on the end of the molecule. So let's see, 1, 2, 3, 4, 5, 6. All right, so that's my terminal alkyne. Now, which reagents would we use to go from a terminal alkyne to an aldehyde? Well, we can use 9-BBN followed by hydrogen peroxide and sodium hydroxide. So that will add a carbonyl to the less substituted carbon on the triple bond. So I can even, here, let's number our carbons just so we can kind of see where everything is. And we're adding that aldehyde to carbon 6. So the less substituted carbon. Okay, so now let's figure out how do we make our alkyne here. That's a funky arrow. So how do we make an alkyne? Well, there's a few different ways we can make an alkyne. In this case, we want our alkyne to end up on the end of a molecule, so this is a little tricky. So what we might need to do instead of, like for instance, maybe you'd be tempted to form an alkyne here and then add more carbons on. But we need that alkyne to be on the end of our 6-carbon chain, so that's not really going to work in this case. What we could do instead is we know that we need an alkyl halide in order to extend a carbon chain, right? So in alkylation, we need an alkyl halide. So what if we turn our alkene into an alkyl halide? Okay, so once we have our alkyl halide, then we can add a triple bond. So this would actually be a substitution reaction where the triple bond is our nucleophile. So this is kind of a different way to approach this chain lengthening type of problem. Okay, so how do we turn our 4-carbon alkene into an alkyl halide? Well, we can add HBr, but do we want the bromine to add to the more substituted carbon or the less substituted carbon? Well, in this case, we probably want it to add to the less substituted carbon because we want the triple bond to attack the carbon on the end of the molecule, and then the leaving group would leave. So we'd have 1, 2, 3, 4, and then we're adding on carbons 5 and 6. So this problem was a little bit trickier. Instead of turning our starting material into a triple bond and then performing alkylation from there, we actually turned it into an alkyl halide. And then we brought in a terminal alkyne to make our 6-carbon chain. But again, we were using those same 2 steps that we talked about earlier. So 1, we turned a 4-carbon chain into a 6-carbon chain. And then 2, we turned an alkene into an alkyne into an aldehyde. All right. So we'll stop here for this video. And this is really the only video that will cover Chapter 11 in your textbook, but we'll also go over some practice problems in the next couple of videos. So we'll get some more practice with synthesis problems. All right. So if you have any questions, just let me know.